vocabulary term is U-substitution. That would be a technique that allows you to integrate composite functions by substituting U for the innermost function. So this lesson is going to be all about U-substitution, and U-substitution is something that's going to help us integrate composite functions like this function right here, f of g of x. We have a function within a function. So U-substitution just takes U and sets it equal to our innermost function. So we're going to set U equal to g of x, thereby rewriting our original composite function as f of u. Now it's in terms of u. Now, why would we do that? Why is that helpful? Well, let's get into it. This theorem, the antidifferentiation of a composite function, says let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable on its domain, and capital F is an antiderivative of f on I, then the integral of f of g of x times g prime of x dx is equal to capital F of g of x plus c. So all this is saying is that if you want to take the integral of a composite function, a function within a function, our innermost function being g of x and our outer function being f, and that is being multiplied by the derivative of your innermost function, g prime of x. That's going to be equal to the antiderivative of your outer function, that would be capital F, of your innermost function, g of x plus c. So this looks super confusing, but it actually makes sense if you think about it as the reverse chain rule. The chain rule says if I have a composite function like this and I take the derivative, what's going to happen is I'm going to take the derivative of the outer function, this capital F, and it would give me lowercase f of g of x. But then I have to multiply by the derivative of my innermost function, g prime of x. That's where this comes from. It's just the reverse chain rule. If I integrate this, I get this. That's what this theorem is saying. Now, let's talk about where U-substitution fits in. Look at this integral right here. That's super convoluted and can sometimes be very confusing depending on what your outer and inner functions are. So what we're going to do is we're going to let U equal that innermost function in here, g of x. That means the derivative of this with respect to x, du dx, is going to be equal to g prime of x. If I then multiply both sides of that equation by dx, I get du is equal to g prime of x dx. Now, why would we do that? Because now we can substitute u in for g of x, and we can substitute du in for g prime of x dx, thereby creating this new integral down here, the integral of f of u du. Now look at this integral compared to this one. Which one do you think would be easier to integrate? Obviously this one. That's where U-substitution comes in. It helps us integrate composite functions much more easily.
There's about 1 million ants for every 1 human. It's example time.
Now example 1 says identify u and du for the integral, then rewrite the integral in terms of u and du. So here we have the integral of 3 times the quantity 3x plus 1 squared dx, and we're asked to do two things: identify u and du, and then rewrite the integral in terms of u and du. So first we want to identify u and du. Remember, in U-substitution we're going to let u equal our innermost function. So the question is, what is our innermost function? Well, we have 3 times something squared, and then that something in here is 3x plus 1. So this is going to be our innermost function in here, 3x plus 1. So we're going to say u equals 3x plus 1. Next, we need to find du. So to find du, all you have to do is take the derivative of your innermost function with respect to x. So the derivative of u with respect to x is du dx. The derivative of 3x plus 1 with respect to x, we take the derivative of each of these, we get 3 plus 0. So du dx is equal to 3. But we don't want du dx, we want du. So we multiply both sides of the equation by dx, and we get du is equal to 3 dx. Now, why is that important? Because if we look at our integral, we now have u equal to 3x plus 1, and du is equal to 3 dx. And notice there's a 3 times dx in the problem. So when I rewrite my integral here, I'm going to substitute u in for that 3x plus 1, and I'm going to substitute du in for 3 dx. So our new integral looks like this, the integral of u squared du. That's why U-substitution is important, because look how much easier this is to integrate than that. Part B, doing the same thing. We have two things we need to do here. We need to identify u and du, and then rewrite the integral in terms of u and du. So first, identify the u and du. U needs to be our innermost function. So here, we have a function, 5 times e to the something, and that something is 5x. So that would be our innermost function in here. So we're going to let u equal 5x. Now the question is, what is du? Well, we take the derivative of this equation with respect to x. So the derivative of u with respect to x is du dx. The derivative over here of 5 5x with respect to x is just going to be 5. We need du though, not du dx. So we multiply both sides of the equation by dx. We get du is equal to 5 dx. Now, why is that important? Why is that cool? Because if we look at our integral, we have a 5 times dx in that integral. So when I rewrite my integral in terms of u and du, we're going to substitute u in for this 5x here, and we're going to substitute du in for 5 times dx. So our new integral looks like this, the integral of e to the u du. And this is clearly much easier to take the integral of than this.
You ever seen that movie, Ants? No, neither did I. You try.
Okay, doing the same thing here. So first, we want to identify u and du for the integral, and we're going to let u equal our innermost function. Oh, well, there's two different x's here. There's two separate functions. So what do? Well, when that happens, what you want to do is you want to set u equal to one of the functions that you know when you take the derivative of that function, your du dx then will equal your other function. So in this case, I'm going to set u equal to 2x squared plus 1. The reason is because when I take the derivative of this with respect to x, over here I get du dx. On this side I get 4x to the first plus 0, or just 4x. Now look, that's the other function in the problem. That's why we chose u to equal 2x squared plus 1, because the derivative of that is equal to that other function, which means if I were to solve for du, I would multiply both sides of the equation by dx, and now du is equal to 4x dx, which takes care of everything else in the problem. So if I were to rewrite my integral, I would substitute u in for 2x squared plus 1, and now I can substitute du in for that 4x dx, creating this new integral u squared du, which clearly would be easier to integrate than this indefinite integral up here. Part B, doing the same thing. First thing I want to do is find u and du. So u, I'm going to set equal to my innermost function. Oh, I have two separate functions here being multiplied together. So when this happens, I need to set u equal to one of the functions, where if I were to take the derivative of that function, my du dx would equal that other function. So which of these functions is the derivative of the other? The derivative of tan x is secant squared x. So what I can do is set u equal to tan x plus 3. Now the reason I include 3 is because when I take the derivative of this, the derivative of 3 turns into 0, and the derivative of tan x is that secant squared x. So if I were to find du, I just multiply both sides of this equation by dx. I get du is equal to secant squared x dx, which takes care of everything else in the problem. That's how you do this. You set u equal to the function that if you were to take the derivative of that, it takes care of everything else in the problem. So now I can rewrite my integral in terms of u and du. I'm going to substitute u in for tan x plus 3, and now I can substitute du in for secant squared x dx, and my new integral is just the integral of u du, which is clearly easier to take the integral of than this up here. Now this theorem, the general power rule for integration, says if g is a differentiable function of x, then the integral of g of x to the nth power times g prime of x dx is equal to g of x to the n plus 1 power over n plus 1 plus c, where n cannot equal negative 1. Equivalently, if u is equal to g of x, then the integral of u to the nth power du is equal to u to the n plus 1 power over n plus 1 plus c, where n cannot equal negative 1. So all this is saying is that you can still use the power rule when you use U-Substitution. So if we substitute u in for g of x and du in for g prime of x dx, and we integrate u to the nth power du, it's still going to be equal to u to the n plus 1 over n plus 1 plus c, just like we normally integrate. Now example 2 says find the indefinite integral. So we're taking this indefinite integral right here. Now, if you look closely at this function, we have a function within a function times another function. So let's try to use U-Substitution in order to more easily integrate this. In order to use U-Substitution, we need to find u and du. So we're going to set u equal to our innermost function. But as we said, there's multiple functions here. So when that occurs, we need to set u equal to whatever function, if I were to take the derivative of it, would equal the other function. So I'm going to set u equal to x squared plus 1. The reason is because if u is equal to x squared plus 1, and I take the derivative of this with respect to x, the derivative of u with respect to x is du dx. Over here, the derivative of x squared plus 1 is going to be 2x to the first plus 0, or just 2x. I then multiply both sides of the equation by dx. I get du is equal to 2x dx. Now look, 2x dx, that takes care of the other function in the problem. So when I rewrite my integral in terms of u and du, I'm going to substitute u in for x squared plus 1, and I can substitute du in for that 2x dx, and I just get the integral of u squared du. That's why we did that. And look, we have an indefinite integral that is clearly much easier to integrate than our original integral. Now, how do I integrate u squared du? Well, I use the general power rule, just like we were talking about. The integral of u squared du is going to be u to the 2 plus 1 power over 2 plus 1 plus c. I then simplify this down and get u cubed over 3 plus c. Now, to finish this question, all I have to do is substitute what I set u equal to back in for u. So I'm going to take x squared plus 1, plug it back in for u in this antiderivative, and I get x squared plus 1 cubed over 3 plus c. I could write this as my answer, or if I want to make it look a little neater, I could just take this divided by 3 and make it a 1/3 multiplied out front, and I have my antiderivative. Done. Part B, doing the same thing. I have an indefinite integral that I want to evaluate, and I now have a function, 5x, within another function, this e. So what I'm going to do is I'm going to use U-substitution in order to evaluate this indefinite integral. To use U-substitution, I need to find u and du. So what am I going to set u equal to? Well, because I have a function within another function, I have a composite function here, I want to set u equal to my innermost function. So I'm going to set u equal to that 5x. Now, in order to find du, I need to take the derivative of this with respect to x. So the derivative of u with respect to x is du dx. The derivative of 5x is just going to be 5. To find du, I multiply both sides by dx. I get du is equal to 5 dx. Now look at that. Du then is going to take care of everything else in the problem, the 5 and the dx. So when I rewrite my integral in terms of u and du, it's going to be the integral of, now I substitute u in for that 5x, so it's going to be e to the u, and then du, I'm going to substitute in for the 5 dx. So I end up getting the integral of e to the u du, which is clearly easier to take the integral of than this. So how do I take the integral of e to the u du? Well, what's the integral of e to the x? That's e to the x plus c. So the integral of e to the u is going to be e to the u plus c. Now all I have to do to evaluate this indefinite integral is take what I set u equal to and plug it back in for u. So I'm going to take 5x, plug it back in for u, and now I have evaluated this indefinite integral.
You ever see a Bug's Life? Great flick! You try!
Okay, doing the same thing. We again need to evaluate an indefinite integral, and this time we have a function within a function being divided into another function. Well, clearly this is going to require some type of u substitution. So we need to figure out what are we going to set u equal to, and then what is our du. We usually set u equal to our innermost function, but in this particular problem we have multiple functions. So what do? Well, we need to set u equal to a function that, if we were to take the derivative of that function, it would equal the other function that's in the problem. So I'm going to set u equal to x squared plus 1, because the derivative of this with respect to x is going to be du dx is equal to 2x. And if I multiply both sides of the equation by dx, I get du is equal to 2x dx. Now look, 2x dx, that's the other part of this indefinite integral. So what I can do then is use u substitution in order to evaluate this integral. Now I can take u, plug it in or substitute it in for x squared plus 1, and take du and substitute it in for 2x dx. Now I have an indefinite integral in terms of u that I can evaluate. In order to evaluate this indefinite integral, I need to prepare it for integration. Now I can integrate this with the general power rule. When I integrate this, it's just going to be u to the negative 3 plus 1 power over negative 3 plus 1 plus c. I simplify that and I end up getting u to the negative second over negative 2 plus c. Now all you have to do to finish evaluating this integral is take whatever you set u equal to, plug it back in for u, and then simplify it. So in our final answer, we don't want to have a negative exponent, so we're going to take this x squared plus 1 to the negative second power, move it back down to the denominator, and we have our indefinite integral. Part B, doing the same thing. We again have multiple functions within the same integral. When that happens, you're going to need to use u substitution. Now, the question is, what are we going to set u equal to? Well, u usually is equal to your innermost function, but we don't have that. We have multiple functions being multiplied together. So what we have to do instead is set u equal to whatever function that, if you were to take the derivative of that, would be equal to the other function in the integral. So what function, if you were to take the derivative of that function, would equal the other function? Well, that would be this tan x plus 3. If I take the derivative of tan x plus 3, I end up getting secant squared x. So I'm going to set u equal to tan x plus 3. That means the derivative of this with respect to x would be du dx is equal to secant squared x plus 0, or just secant squared x. Multiply both sides by dx, I get du is equal to secant squared x dx. So if I were to rewrite this indefinite integral in terms of u and du, it would be equal to the integral of u du, because I substitute u in for tan x plus 3, I substitute du in for secant squared x dx. Now all I have have to do is use the general power rule to evaluate this indefinite integral. So using the power rule, the integral of u du is going to be u to the 1 plus 1 power over 1 plus 1 plus c, or u squared over 2 plus c. Now that I've taken the integral, all I have to do to answer this question to find the indefinite integral of this function is plug back in whatever I set u equal to. So I'm going to take that tan x plus 3, plug it back in for u, and I could leave this as my answer. Or if I want to make this look a little neater, instead of writing all of this divided by 2, I could just take that, move it out front, and make it 1/2 times tan x plus 3 squared plus c. Now, example 3, I am again finding the indefinite integral, this time of e to the x plus 1, the quantity, times e to the x plus x, the quantity dx. Now, I clearly have multiple functions in this one indefinite integral, so I need to use U-substitution. The only question is, what am I going to set u equal to? Well, I usually set u equal to my innermost function, but here, I don't have an innermost function. I have two functions being multiplied together. When that occurs, I need to set u equal to whichever function. When I take the derivative of that function, I get the other function. So in this particular integral, I would set u equal to e to the x plus x. The reason is because if I take the derivative of this with respect to x, I get du dx is equal to the derivative of e to the x is just e to the x. The derivative of x is 1. Then I multiply both sides by dx, I get du is equal to e to the x plus 1 dx. So you see that if I set u equal to e to the x plus x, du is going to be equal to e to the x plus 1 dx. It takes care of the other function. So now if I want to rewrite this integral in terms of u and du, all I have to do is substitute u in for e to the x plus x, and then substitute du in for e to the x plus 1 dx, and I have the integral of u du, which is clearly easier to evaluate than this indefinite integral up here. So now I evaluate this integral using the general power rule. The integral of u du is going to be u to the 1 plus 1 power over 1 plus 1 plus c. I then simplify that to u squared over 2, and now all I have to do to finish evaluating this indefinite integral is take whatever I set u equal to and plug that back in. So e to the x plus x, I plug back in for u. I could leave this as my answer, or if I want to make it look a little neater, I could take that divided by 2, move it out front, and make it 1/2 times e to the x plus x, the quantity squared, plus c. Part B, doing the same thing. I have multiple functions being multiplied together in the same integral. Because of that, I need to use U-substitution to help me integrate this. So what am I going to set u equal to? Well, I usually set u equal to my innermost function. In this case, that would be x cubed minus 2. But I also have another function in this. So I need to set u equal to whichever function, when I take the derivative of that function, it equals the other function. It takes care of the other function. That's still x cubed minus 2. Because if u is equal to x cubed minus 2, and I take the derivative of this with respect to x, I get du dx is equal to 3x squared plus 0, or just 3x squared. Multiply both sides by dx, I get du is equal to 3x squared dx, which takes care of everything else in the problem. So all I have to do then is rewrite this integral in terms of u and du. So I'm going to substitute u in for x cubed minus 2, substitute du in for 3x squared dx. This is my new integral in terms of u and du. Much easier to evaluate than this integral up here. So now all I have to do to evaluate this integral is use the general power rule. But what do I do with this square root? Remember, I rewrite it as a rational exponent, as u to the 1/2 power. Now all I have to do is use that general power rule to evaluate this integral. It's going to be u to the 1/2 plus 1 power over 1/2 plus 1 plus c. I simplify, and dividing by 3/2 is the same as multiplying by 2/3. So I have now evaluated this indefinite integral. But the question wanted me to evaluate this indefinite integral, so my answer needs to be in terms of x. So what I do is take what I set u equal to, x cubed minus 2, plug it back in for u, and I have my answer. Now, there are a couple special cases we need to talk about. The first one looks like this. So we again have a function multiplied by another function that is within a function. So we clearly need to use U-substitution. In order to use U-substitution here, we got to figure out what are we going to set u equal to. Well, in this case, we typically set u equal to our innermost function, but we also have another function being multiplied to this function. So we need to make sure that we set u equal to whichever function that, when we take the derivative of, gives us the other function. So I'm going to set u equal to x squared plus 1. The reason is because if u is equal to x squared plus 1, and I take the derivative of this with respect to x, I get du dx is equal to 2x to the first. And when I multiply both sides by dx, I get du is equal to 2x dx. But in this problem, you look and you see, okay, yeah, there's an x and there's a dx, but there's no 2. So what do I have to do about that? Well, what you're going to do anytime this occurs is you're going to take this 2 and divide it to the other side. So we end up getting that 1/2 du is equal to x dx. Because we can only substitute substitute in for exactly what's there. And what's there? X dx. So we have to make sure that it's equal to x dx. So now we can rewrite our integral in terms of u and du. We're going to substitute u in for x squared plus 1. We're going to substitute 1/2 du in for x dx. And look, we have an indefinite integral in terms of u and du. That is clearly much easier to integrate than our original integral. Now, what do we do with this 1/2? Well, it's just a constant. So all we have to do is just take that, move it out front, and we'll multiply it on at the end. So what is the integral of u squared du? We just use the power rule. So the integral of u squared du is going to be u to the 2 plus 1 power over 2 plus 1 plus c. Make sure you keep that 1/2 multiplied out front. We simplify and we end up getting u to the 3rd over 6 plus c. Now, we want to evaluate this indefinite integral, which means our answer needs to be in terms of x. So what we're going to do is we're going to take whatever we set u equal to, in this case it was x squared plus 1, plug it back in for u, and then simplify. Technically, you can leave this as your answer, or if you want to make it look a little neater, instead of writing divided by 6, you can multiply a 1/6 out front, and you have your answer. Part B, we have an indefinite integral of a function within another function. So it looks like it requires U-substitution. So we're going to set u equal to our innermost function here, which would be x squared plus 1. That means in order to get du, we're going to take the derivative of this with respect to x. So it's going to be du dx is equal to 2x to the first plus 0. So just du dx is equal to 2x. Multiply both sides by dx, we get du is equal to 2x dx. We look at this problem, there's only a dx. There is no x here. This means we cannot use U-substitution. Anytime your du is equal to some variable times dx, and that variable does not exist in the problem, there's no other x here that we can substitute in for, we cannot use U-substitution. We got to find another way to evaluate this indefinite integral. So how do we do this? Well, let's rewrite x squared plus 1, the quantity squared, as x squared plus 1 times x squared plus 1. Now all we have to do is FOIL this out, and we end up getting a function with multiple terms. And anytime you're integrating a function with multiple terms, you can just integrate each term separately. So that's what we're going to do. Here, the integral of x to the 4th dx, we use the power rule. It's going to be x to the 4 plus 1 power over 4 plus 1 plus c. Here, the integral of 2x squared dx. The 2 hops out front, and you just integrate x squared dx, which is x to the 2 plus 1 power over 2 plus 1 plus c. We integrate 1 dx. The 1 you can technically take out front, or you can just integrate. It just becomes x plus c. Add up all the constants of integration just to create one constant of integration, and simplify. We end up getting our indefinite integral up here is equal to 1/5 x to the 5th plus 2/3 x cubed plus x plus c. Now, example 4, we are again finding the indefinite integral. So here we have a function within another function times another function. So this clearly requires U-substitution. So the question is, what am I going to set u equal to? Well, in this case, because we have a function multiplied to another function, we want to make sure we set u equal to whichever function. If I were to take the derivative of that function, would include the other function. So in this case, I'm going to set u equal to x squared minus 5. The reason is because if I take the derivative of this with respect to x, I get du dx is equal to 2x to the first minus 0, or just 2x. Multiply both sides by dx, I get du is equal to 2x dx. Now we look at the problem. There's an x and there's a dx, so that takes care of that in the problem. But there is no 2. What do we do when that happens? We take this 2 and we divide both sides by 2, because we can only substitute in for exactly what's there, x and dx. Now what I can do is rewrite this indefinite integral in terms of u and du. I'm going to take u and plug it in for x squared minus 5. I'm going to take 1/2 du and plug it in for the x dx. I now have rewritten this indefinite integral in terms of u and du. Now, how do I integrate this? Well, this 1/2 is just a constant. I can move out front, and now all I have to do is integrate u squared du using the general power rule. The integral of u squared du is going to be u to the 2 plus 1 power over 2 plus 1 plus c, which simplifies to u cubed over 3. Multiply that to the 1/2 that was out front, and I end up getting u cubed over 6 plus c. Now all I have to do to evaluate this integral up here is take what I set u equal to, x squared minus 5, and plug it back in for u. When I do that, I can write this as my answer, or if I want to make it look a little neater, I can take this divided by 6 and rewrite it as multiplying by 1/6 out front, and I end up getting my indefinite integral. Part B, doing the same thing. I have a function within another function, so I'm going to need to use U-substitution. So the first step in U-substitution is figuring out what are you going to set u equal to. Well, in this case, I have a function within another function, so I can just set u equal to my innermost function. So I'm going to set u equal to 2x minus 1. Now I need to find du, so I'm going to take the derivative of this with respect to x. I get du dx is equal to 2 minus 0. Multiply both sides by dx, I get du is equal to 2 dx. We look at the problem, there's a dx, but there is no 2. So when this occurs, I just divide that constant to the other side, and I get 1/2 du is equal to dx. Now I can rewrite this indefinite integral in terms of u and du. So I'm going to substitute u in for 2x minus 1. I'm going to substitute 1/2 du in for dx. I have now rewritten my integral in terms of u and du. So I need to evaluate this integral now. To do that, I need to prepare this for integration. I'm going to take this 1/2, move it out front of the integral sign. I'm going to rewrite the square root of u as u to the 1/2 power. That way I can just integrate using the general power rule. The integral of u to the 1/2 du is going to be u to the 1/2 plus 1 power over 1/2 plus 1 plus c. I then simplify this and I end up getting my evaluated definite integral right here as u to the 3/2 over 3 plus c. Now to answer this question, I need my answer to be in terms of x. So I go ahead and plug back in what I set u equal to. I take 2x minus 1, plug it back in for u, and I have evaluated this definite integral up here. But if I want to make it look a little neater, instead of dividing by 3, I could just rewrite this as 1/3 times the quantity 2x minus 1 to the 3/2 plus c. Now example 5, we're again finding an indefinite integral. This time we have a function within a function within another function times a function within a function. Wow. So this is clearly going to require u substitution, meaning I need to figure out what's my u, what's my du. So what am I going to set u equal to? Well, anytime you have a function times another function like this, you want to set u equal to whichever function, if you were to take the derivative of it, would give you the other function. Well, cosine is the derivative of sine, but this is sine squared 3x, which is the same as sine of 3x, the quantity, squared. So what we're going to do is we're going to let u equal sine of 3x. So I'm going to take the derivative of this with respect to x. I get du dx is equal to cosine of 3x times the derivative of 3x by the chain rule, which is 3. Then when I multiply both sides by dx, I get du is equal to 3 cosine 3x dx. Now I look at our integral and we have a cosine of 3x dx. The only issue is there's no 3. So what I do instead is I take that constant and divide it to the other side, giving me 1/3 du equal to cosine of 3x dx. Remember, I have to substitute in for exactly what's there. Now what I can do is I can rewrite this integral in terms of u and du. So I'm going to substitute u in for sine of 3x. I'm going to substitute 1/3 du in for cosine of 3x dx. Now I have rewritten my integral in terms of u and du, so I can prepare this for integration. I'm going to take this 1/3, which is a constant, just move it out front, and then I can integrate using the general power rule. So the integral of u squared du is going to be u to the 2 plus 1 power over 2 plus 1 plus c. I then simplify and I end up getting u cubed over 9 plus c. But in order to evaluate this indefinite integral, my answer should be in terms of x. So what I'm going to do is I'm going to take what I set u equal to, sine of 3x, plug it back in for u, and I have my answer. If I wanted to rewrite this to make it look a little neater, I could take this divided by 9, move it out front, and make it 1/9 sine cubed of 3x plus c. Now here, we have a special case, something that comes up, not very often, but sometimes. But I want you to be ready because it has appeared on the AP test. So here's how this works. We have an indefinite integral of a function being divided by another function within a function. So we clearly need to use u substitution in order to evaluate this indefinite integral, meaning we need to find our u and du. So in this question, we don't just have a function within another function. We have a function within a function that's being divided into another function. So anytime you have multiple functions being either multiplied or divided, you need to set u equal to whichever function that when you take the derivative of that, you get the other function. Now the only problem is in this question, that doesn't happen. If I set u equal to 2x minus 1, then du is going to be equal to 2 dx. That doesn't take care of this. If I set u equal to x, then du is equal to dx. That doesn't take care of this. So when this occurs, here's what you're going to do. I'm going to set u equal to the square root of 2x minus 1. Now the reason I'm going to do that is because normally I would just take the derivative of this with respect to x. Over here, this would get super messy. It would be 1/2 2x minus 1 to the negative 1/2 power times the derivative of what's in here. That won't help us substitute in for x and dx. So by setting u equal to the square root of 2x minus 1, what I can do instead is solve this equation for x, and I can get something in terms of u that I can substitute in for x. So how do I solve this equation for x? I square both sides of the equation, I add 1 to both sides, multiply both sides by 1/2, and I end up getting that x is equal to 1/2 u squared plus 1. Now I can plug in this 1/2 u squared plus 1 for x up here. So the only other thing that I have to make in terms of u is this dx. So how do I figure out what dx is? Well, I need to take the derivative of this now with respect to x. I'm not going to take the derivative up here with respect to x because we have a square root here. It's going to get a little messy. So let's take the derivative here with respect to x. When I take the derivative of this side with respect to x, I just get 1. When I take the derivative of this side with respect to x, the 1/2 is just a constant. It stays out front. So I take the derivative of each term in here with respect to x. The derivative of u squared with respect to x is going to be 2u, and because it's with respect to x, I have to multiply by du dx according to implicit differentiation. The derivative of 1 is just a constant, so that's just going to be 0. So I end up getting 1/2 2u du dx is equal to 1. But remember, I'm trying to get dx in terms of u and du. So what I need to do is get dx by itself in this equation. So I'm going to multiply both sides of the equation by dx. Now over here I could simplify the 1/2 and the 2, and I end up getting dx is equal to u and du. So I can now rewrite this indefinite integral completely in terms of u and du. I can plug in u for the square root of 2x minus 1. I can plug in 1/2 the quantity u squared plus 1 for this x, and for dx I can plug in u and du. So that's what I'm going to do. I'm going to rewrite this indefinite integral in terms of u and du now. Now all I have to do is evaluate this integral, and to do that I need to prepare it for integration. I need to simplify in here. There's a lot going on. So what can I simplify? Well, this u here cancels out with this u in the denominator, which is nice. This 1/2 is just a constant. I can move out front of the integral, and now all I have is 1/2 the integral of u squared plus 1 du, which is pretty easy to integrate because all I have to do is integrate each term in here separately. The integral of u squared du is going to be u to the 2 plus 1 power over 2 plus 1 plus c. The integral of 1 du is going to be u plus c. The c's add together to create just one constant of integration, and I distribute that 1/2 out front to each of the terms, and I end up getting u cubed over 6 plus u over 2 plus c. Now to finish evaluating this indefinite integral, what I'm going to do is I'm going to take what I set u equal to, the square root of 2x minus 1, and plug it back in for u in what I got over here. Now you could leave this as your answer, but we typically don't leave radicals raised to an exponent. We normally rewrite that as a rational exponent. The square root of 2x minus 1 is 2x minus 1 to the 1/2 power, which is being raised to the 3rd power. So power to a power, we multiply 1/2 times 3, we get the 3/2 power. Over here, the square root of 2x minus 1, we just know is 2x minus 1 to the 1/2 power. We bring each of these denominators out front and write it as a fraction, and you're done.